When you hear the word gravity, you probably think of an invisible force that keeps us grounded on Earth, right? Well, hold on to your seat, because a groundbreaking discovery has shaken up that very idea. It turns out, gravity might not be a force at all, at least not in the way we've always thought. This revelation is one of the biggest shifts in our understanding of physics in centuries, and it has the potential to change everything we thought we knew about the universe. A new perspective: gravity as curvature, not force. For most of human history, gravity has been one of the most straightforward concepts in physics. It's the invisible force that keeps our feet planted on the ground, causes objects to fall when dropped, and governs the orbits of planets. We've known about it for centuries, thanks to Sir Isaac Newton, who first described gravity in the 17th century. According to Newton, gravity was an invisible force that attracted objects toward one another. It was simple and intuitive, and it worked. If you drop something, it falls. If you jump, gravity pulls you back down. But what if everything we thought we knew about gravity was just part of the story? In the 20th century, Albert Einstein introduced a mind-bending theory that would forever change the way we understand gravity. Einstein's theory of general relativity, published in 1915, turned everything we thought we knew upside down. Rather than thinking of gravity as a force, Einstein proposed that gravity is actually the result of the curvature of spacetime, an entirely different way of viewing the forces of nature. Instead of seeing gravity as a mysterious force pulling objects together, Einstein's theory suggested that massive objects like the Earth, the Sun, and even black holes cause a distortion in the very fabric of space and time itself. What does curvature mean? Let's pause for a moment and break this down. Imagine the fabric of space-time as a stretched-out rubber sheet. If you place a heavy object, like a bowling ball, in the center of that sheet, the fabric bends around it. In the universe, this analogy helps us understand what's happening on a much larger cosmic scale. Planets, stars, and other massive objects bend the fabric of space-time around them in a similar way, creating what we experience as gravity. Instead of thinking of gravity as a force pulling objects toward each other, it's more accurate to think of it as the natural movement of objects through curved space-time. When you're standing on Earth, you're not being pulled by Earth's gravity. How did Einstein get there? So, how did Einstein come to such a radical conclusion? To answer that, we need to think about how gravity was understood before Einstein. Newton's view of gravity worked for centuries. It explained the motion of planets and objects on Earth perfectly. However, it had some limitations. For one, Newton's laws didn't account for the speed of light, or for how gravity might affect light itself. Einstein's general relativity solved these problems by proposing that space and time aren't fixed and rigid as Newton believed. Instead, they are part of a dynamic, flexible structure that can bend and stretch. This bending, or curvature, is what causes gravity. One of the most famous predictions of general relativity was that light, which travels at the fastest speed possible, would bend around massive objects like stars. This was later confirmed in 1919 when astronomers observed that starlight passing near the Sun was indeed bent, proving that gravity affects light as well. Why this matters. A new lens on the universe. The discovery that gravity is not a force but rather a result of the curvature of space-time isn't just a tweak to our understanding of physics. It's a game changer. This revelation doesn't just change how we think about gravity, it changes the very way we see space and time. So why does this matter so much? To put it simply, if gravity is not a force, then the universe we live in is far more complex and mind-boggling than we ever imagined. And if gravity can be explained as the curvature of space-time, what else could be lurking under the surface of our current understanding? Einstein's breakthrough has opened the door to a whole new realm of questions that could redefine everything from the origins of the universe to the very nature of reality itself. Let's take a deeper dive into why this shift in perspective is so important: the complex nature of the universe. The idea that gravity is the result of the curvature of space-time is so groundbreaking because it suggests that the universe is far more intricate than the straightforward model we've had for centuries. Before Einstein, we saw the universe as a collection of objects, planets, stars, and galaxies, floating in a vast, static space. Gravity was simply the force that connected everything, pulling objects together. But Einstein revealed that space and time themselves are not rigid backdrops. This new understanding challenges the very fabric of our reality. The idea that gravity is a consequence of space-time curvature begs a powerful question. What else could our current model of physics be missing? What other aspects of the universe, hidden from view, could be revealed through this new lens? Perhaps we've only scratched the surface in understanding how the universe functions. This discovery pushes us to think bigger and to consider that the universe may hold far more mysteries than we ever expected. The idea that space and time are not fixed, but dynamic and fluid, means that everything we thought we knew about the structure of the cosmos is subject to revision. The behavior of light around massive objects. Another area where Einstein's theory has opened new doors is in our understanding of how light behaves around massive objects, like stars or black holes. According to General Relativity, light should bend when it passes near massive objects. This is called gravitational lensing. If gravity is not a force pulling on light, but rather a bending of space-time, this changes how we think about the interaction between light and gravity. We may be able to observe and measure these effects more accurately: energy and mass. The ripple effect. How Einstein's theory changed everything. When Albert Einstein published his theory of general relativity in 1915, he didn't just tweak our understanding of gravity, he fundamentally reshaped the entire framework of physics. Instead, it's the result of massive objects warping the very fabric of space-time itself. It's not an exaggeration to say that this was a game changer. Imagine, for a moment, having the lens through which you view the entire universe turned upside down. And yet, over 100 years later, we're still exploring the ripples this discovery created. A new lens on gravity. When you think about gravity, it's easy to picture an invisible force that pulls you down to Earth. But that's not the whole story anymore. Think of space-time as the fabric of the universe, and massive objects like stars and planets as weights placed on this fabric. The heavier the object, the more it warps the fabric. Other objects, like satellites or even light itself, move along these curves in space-time. Space and time are no longer separate entities. They're intertwined in a single, malleable fabric that responds to the presence of mass and energy. This insight has implications far beyond just gravity. It influences how we think about black holes, the behavior of light, and even the passage of time itself. Thanks for watching. Please like the video, press the subscribe button, and also drop your thoughts in the comment section.